Hi, good morning, good afternoon, everyone. My name is Jeremiah Johnson. I'm faculty at North Carolina State University, and I'll be the moderator for today's panel. We'll start with brief introductions for our panelists here. I'll lead them with some questions, and we'll have a discussion for a bit, but I'll be sure to save time for audience Q&A. And the webinar is set up so that we can receive written questions and that I will read back to our panelists. Let me start with introductions here. First, I'd like to introduce Professor Valeria Karplus. She's an associate professor at Carnegie Mellon University in the Department of Engineering and Public Policy. Her research interests include decarbonization of global corporate and industrial supply chains, regional approaches to low carbon transitions, and integrated design and evaluation of air, energy, and climate policies. At CMU, she also runs the Lab for Energy and Organizations at the Scott Institute for Energy Innovation. And some time ago, she was the co-founder and director of the MIT Tsinghua China Energy and Climate Project. Our second panelist, Eric Masanet, holds the Duncan and Suzanne Mellichamp Chair in Sustainability Science for Emerging Technologies at UC Santa Barbara. His research develops energy and materials system models to identify technology and policy pathways for decarbonizing industrial systems. He has held positions where he has led the Energy Demand Technology Unit at the IEA, overseeing energy analysis on global industrial, transport, and building sectors. And he is a lead author for the Demand Working Group, the Demand chapter of Working Group 3 of the IPCC 6th Assessment Report, and on the advisory board for ACEEE. Past experience includes time as faculty at Northwestern University, as well as the International Energy Studies Group at Lawrence Berkeley National Lab. And finally, our third panelist, Chris Bataille, joins us from Simon Fraser University and Columbia University, where he is involved in the Center on Global Energy Policy and focusing on industrial decarbonization. He has been involved in energy and climate policy for decades, doing research on energy systems and economics modeling, serving as an analyst, a writer, a project manager, a consultant, and a founding partner. He is also a associate researcher at the Institute for Sustainable Development and International Relations, working on the Deep Decarbonization Pathways Project. Also a lead author of the 6th Assessment Report, focusing on the industry chapter, and manages a number of ongoing projects, including the Net Zero Steel project. So an absolutely incredible panel. I would also like to thank Professor John Wyatt from Stanford University for joining us today, and Polly Ann from Stanford for helping us facilitate this great panel on industrial decarbonization. So I'm going to ask our panelists to provide some brief opening remarks structured around the question, you accepted our invitation to speak on this topic of decarbonization of heat and industrial processes. Why is this topic rather worth your time and attention? Valeria, could I start with you, please?
Absolutely. Yeah. So I guess I would rephrase the question to say, why is, how could this topic not be worth your attention, especially now, and especially given the interest in transforming our economy in a low carbon direction that includes all sectors and has a big emphasis on manufacturing and infrastructure. And that's true for many of the plans around the world. I think we're going through a period of, in some ways, of retreat from globalization, and so as we think about decarbonizing the industrial sector, I think we have to still think about it in a global picture, but also with these national priorities in mind. So from my perspective, as someone who works across levels, from sort of the macro government policy decision making through the energy system models down to sort of the micro firm behavior, I'm really interested in what enables decisions to decarbonize industry sort of at the in the boardroom, but also on the factory floor. And so I think thinking carefully about how better models can enable better decision making in these areas. And so I think that the technology is fascinating and challenging. There's a lot of in many ways I see lot of interesting frontiers for innovation, but we have to make sure also that our modeling and sort of policy thinking is keeping up and supporting that. And so this sort of multi-sided problem is the type that I really gravitate towards. So thank you for the opportunity to join.
Thank you so much, Valerie. And I think you really speak to a lot of the audience members right now. You know, we really do want to enable better decision making, and pointing out that those decisions happen in so many different venues with so many different decision makers is really important. Thank you. Eric, why did you join this panel?
Well, first, thanks for the invitation to join you today. I'm really excited about it, and I've been looking forward to this panel for a while. So just to build on Valerie's comments, for context, you know, I just wanted to point out that where we are today is a huge step forward when it comes to industrial decarbonization. It's finally getting the attention and urgency that it deserves from the policy community, the research community, from the business sector, but even the public, right, is now aware of industrial decarbonization. And it wasn't always the case. You know, prior to the Paris Agreement, when the world was aiming for a 2-degree warming target, most of the models and ambitions that were out there for the industrial sector were frankly pretty simplistic, right? 2 degrees implied we could still have some residual emissions, and mostly those were reserved for the industrial sector. And most decarbonization plans focused on efficiency, maybe a few emerging technologies, the easy stuff, and then lots and lots of CCS for the industrial sector. But that's clearly changed with net zero ambitions. You know, there's no path to net zero without fully decarbonizing the industrial sector. So not only is there more urgency on the policy and investment side, in the modeling community, which is where I sit, suddenly there's just a huge step forward in terms of the interest in the sector, the people that are working on it, the data sources, the modeling techniques. It doesn't mean we've got it all under control, but for me, this is really kind of a watershed moment for industrial energy and climate modeling, given the urgency and the interest. And you know, the other thing is, just to be fair, it's not that in the past, you know, modelers were being lazy about attacking the industrial sector. It's very difficult, right? I mean, this is a sector that's very heterogeneous. There are, you know, many different industrial subsectors, many different processes, many different products. To come up with a decarbonization plan, we need to think about many options: efficiency, fuel switching, electrification, demand reduction, CCS, many solutions, and those solutions will look different depending on the industry and the location. So it's pretty tough stuff, but I feel like the community is now rising to the challenge, and it's just a very exciting time. So any chance that I get to participate in these conversations, I jump at, and especially to learn from, you know, some of the colleagues here and from the discussions. I just find it a lot of fun. So I think it's a good time for us as a panel to really highlight the importance of this sector, and also maybe, you know, inspire some young analysts to start working on this industry, this part of industrial of energy models, because the industrial sector, its time has come, and it's our moment to seize.
Eric, thank you so much, and thank you for bringing this enthusiasm. I couldn't agree more with the sentiment that the conventional wisdom really has changed. You know, I do feel like not long ago there was this attitude that we would save any of those residual emissions for this sector, so it was okay. And that is certainly not the zeitgeist right now. You know, we need to get these emissions down to zero. Chris, why did you join this panel? Thank you for joining.
Yeah, no, my pleasure. I'm very happy to be here today. So Eric and I, whenever we end up in the same place, we end up saying almost the same thing. So my prepared remarks were almost identical to what he just said. So I'm going to try to be additive to that. Expanding on a couple of the things here, you know, all sectors now have to get to net zero. There is no wiggle room at the end. There is no, you know, negative emissions coming from biomass combustion with CCS that, you know, that the rest of industry can live on. That means that the current generation of plants that we're building likely will be operating in 2050, and anything after 2030 will be operating. So ideally speaking, if we could go really fast, you know, we have this decade of opportunity such that if all new facilities by the early 2030s were near zero emissions, the industrial sector would be in that 1.5 to 2C window, and that is, you know, the objective right now is to do that really fast innovation, exploration, commercialization, such that it becomes standard practice by that point. Now, this is not as heavy a technological lift as I think a lot of people think it might be. An enormous amount of work was done in the 1970s and 1980s. There are PhD theses lining shelves that addressed a lot of this stuff. About 80–90% of the necessary technology for at least the first generation of plants was thought through then. And what I found after Paris, like I was part of something called the Deep Decarbonization Pathways Project. I went through, and all the industrial models kind of stopped at about -50, or they had a lot of CCS. What Eric was just saying is like, is that really the case? So I ended up going on a bit of a tour of having a lot of conversations globally, going on a tour of the literature, and you find all this stuff out there. Hydrogen DRI was first thought of in the 1970s. A lot, CCS is basically an outgrowth of existing oil and gas technologies. We may have made a mistake trying to do it with coal, like do a coal generation of electricity instead of just bolting it on the back end of concentrated CO2 flow coming out of existing sources. The biggest thing, though, that emerges from all of this, and I think this is going to emerge from the conversation, is a lot of this stuff, it's risky. Industrial firms are notoriously conservative and risk averse, and they have to be, because if anything goes wrong, the costs are in hundreds of millions of dollars, if not billions. They're very CapEx heavy. These facilities last a long time. They're very trade exposed. So, if you don't have a market for green materials or inputs to sell into that's willing to pay the initial premium, you're selling into a heterogeneous market where people just can't tell green steel from dirty steel. They can't tell green clinker from dirty clinker. And so you simply can't recover your cost premium, and you simply won't build the facility. So I think our big challenge in this coming decade is to structure policy models. How do we cover that upfront CapEx? How do we cover the operating? How do we get those first 1 to 3 plants built, then the 5 to 10 that takes it to the point by the early 2030s that we can make this, standard practice going forward? And, I'm sure we're going to explore this on the call.
Excellent, Chris. And I really appreciate this sentiment and this idea of getting the incentive structure right when we're facing risky capital intensive choices that feel fundamentally different, or at least quite a bit different than the choices consumers are facing when they are considering an EV, or utilities are facing even with utility scale renewable projects. This does feel different. And how do we get this right? Well, thank you all so much for joining us. I'm going to switch to perhaps some more targeted questions. I'm going to start with Eric, if that's okay. Eric, you recently published a study where you estimated the electrification potential for industrial boilers and quantified the associated climate benefits. I was hoping you could briefly walk us through what you see are the opportunities, what you see are the obstacles, and what you see are the limits of boiler electrification.
Thanks, Jeremiah. Yeah, it's a great question. And, there's a big movement now to leverage electrification in all of the end use sectors, including industry. So one of the motivations for this study was to look at what would seemingly be a pretty straightforward solution, which is electrifying standalone conventional boilers. So just for context, in the US manufacturing sector, these boilers represent about 15% of direct fuel use. So, it's not a silver bullet for decarbonizing the industrial sector, but it's something for which we have a readily available technology. Electric boilers are now very cost competitive. They come in a range of capacities. They have many benefits compared to combustion fuel boilers, like lower maintenance, no need for permitting because there are no combustion emissions, and the list goes on. So we really were looking at, well, if we had this kind of off-the-shelf, ready-made drop-in solution, how quickly could it be rolled out, and how much could it save as one strategy for decarbonizing industry? So the way we approach this, as a modeling team, is first, looking at the data, right? And so there's probably very few technologies in industry or even in society that are older than the steam boiler, right? So, this technology has been around for more than, decades and decades, more than a century. But we know surprisingly little about the installations of boilers in the US. So there are a lot of data barriers. So that's one thing that we always face in the analyst community, and there are ways of overcoming that. So we found that we had to construct our own kind of custom database by looking at EPA air permits, sales data, a whole range of other information sources to even get a sense of, well, just how many boilers are out there. Where are they located? That matters, because the grid matters for, climate change mitigation. What are their capacities? What are their fuels? Which industries are they operating in, and so forth, right? So I think probably the biggest contribution of that study, and which comes along with a lot of studies like this that my colleagues and I do, is creating the data infrastructure that can then be used to inform decisions. So just understanding the boiler space was a challenge. The second thing that was very important was to, as Chris alluded to, is to work with the industry to get out and listen to, understand how boilers are used, understand what their thoughts are on electrification, understand what their barriers are, because we found that there are quite a few barriers. On paper, it seems like, this is an off-the-shelf drop-in solution that can go anywhere where there's a boiler out in industry. In some cases, that's true. If you have a small boiler, it's at the end of its life, and it's cost-effective, firms are already adopting electrified boilers. However, there also are barriers, right? Some industries have a lot of byproduct fuels. So syngas in the chemicals industry, wood waste and black liquor in the pulp and paper industry. If you electrify those boilers, then you got to do something with those byproducts, and those byproducts are part of their overall, operating system, right? They figured out how to integrate those byproducts seamlessly into their overall production system, and then they'd be stranded. There's a lot of CHP out there. CHP means firms are using steam, they're generating steam and electricity at the same time. So if you just electrify the steam portion, suddenly you strand a CHP unit that is a massive investment, and you no longer have on-site electricity generation. Another barrier we heard was that some firms just weren't able to get the available power capacity, or they didn't think they could get it easily in order to electrify their boilers, because in some industries it really raises the electric load. So there are implications for the grid. All of that aside, we did find that there is a pretty big opportunity space for electrifying conventional drop-in boilers. But like everything else in the industrial sector, it has to be transitioned in over time. And the reason is, there are a lot of boilers tend to last decades, right? There are boilers out there that are 50, 60, 70 years old. It's going to take time for those to turn over. So just like Chris said, the plants we have today are going to stick around for a while, right? So there are some industries that use small package boilers that can easily electrify, and those are the priorities to get at first, right? We also need to make sure that we're electrifying kind of in parallel to a greener electricity grid. It doesn't mean that we shouldn't electrify because we have a dirty grid today, right? Most states are moving towards much cleaner grids, so those investments still make sense today. But the savings aren't immediate in some locations because of frankly carbon-intensive electricity grids. But we did find that there's a fairly large segment to the space that's locked up with byproduct fuels and CHP units. And that steam won't be easy to electrify unless we take the next step and figure out what are some strategies for using byproduct fuels. Can they be exported? Can they be repurposed? Will they still be burned and kind of negate some of the savings that are coming from electrifying the boiler in the first place? And then, of course, CHP, right? CHP is a wonderful technology that helped the US and a global manufacturing sector become a lot more efficient over the last several decades, right? But these are huge investments, and once they're in place, they're going to stick around for a while, because now you're making both electricity and steam from the same purchased fuel source. And if it's a byproduct fuel, it makes the challenge even a bit harder. So what to do about CHP, I think, is one of the next frontiers we need to tackle for decarbonizing industry. Because if we take away CHP, we take away potentially the opportunity to burn byproduct fuels, but also to generate electricity on site. So not only are we raising the electricity load from electrifying the steam portion, now we're purchasing more electricity to make up for what we didn't generate in the first place. So there are big grid implications to that. So, to sum up, big opportunity space, like everything else in industry, it's very nuanced. There are early stage opportunities that make sense today, but there are bigger picture problems that speak to how complex this sector is that need to be tackled through additional research, additional policy support in order to fully electrify, all boilers moving forward.
I appreciate this so much, Eric, and I think from the energy modeling point of view, it's easy to get caught in simplifications where we think, okay, if the technology cost of electrifying boilers reaches a certain threshold, we will do it. And I appreciate you laying out some of these obstacles. Byproduct CHP, power capacity into the facility. Could you offer us even just a qualitative sense of scale of these constraints? So you mentioned 15% of direct fuel use is used in this space. Do these obstacles stand in the way of most of this potential, or are these highly specific and small in number?
So they're small in number, but large in terms of the overall share of energy use, at least in the U.S. manufacturing sector. So, there's really no one. So looking at industry requires, thinking about subsectors: pulp and paper, steel, cement, chemicals, and so forth, because they're all unique. So, my go-to resource for answering questions like this is always the DOE's, energy and emissions footprint, the latest data. So I'm looking at it now, and so there's about 3 times as much fuel that goes into CHP units in U.S. industry as goes directly into standalone boilers. So that gives you a sense of the scale. So, and like I said, this was done for a reason, right? It's much more efficient to, generate on-site steam and electricity in parallel than it is to generate steam in a boiler and buy from the grid. And this has been a big policy push in the US and globally for a long time, and it's a big success story. But now what it does is it creates a barrier for electrifying end uses, because if you change one of those, let's say energy vectors, the steam side, you reduce it through efficiency or electrify it. So what do you do if you have a CHP unit? You either turn it down and it runs less efficiently and now you're generating less steam, or you continue to burn the same amount of fuel and you vent some steam, right? Those are both kind of suboptimal solutions. It doesn't mean there isn't a path forward. It's just we haven't tackled it yet. So, it's concentrated in a few industries, no doubt: pulp and paper, the food industry, the chemicals industry, but these are really large in the context of US energy use. And it's something that I think the policymakers, investors, manufacturers, and the modeling community needs to confront with a little bit more nuance, just to see what the barriers are and how we move forward.
I appreciate that. Thank you. I think as we march through these constraints, as we march through these challenges, this heterogeneity of this space, I do have kind of an underlying concern that maybe we get these things right and we develop this policy that actually respects all of these challenges, but we do it as a domestic policy, and we fail to capture the big picture that we can't do it as a single country alone, we being any country. Valeria, I'd like to ask you the next question here. So given the extent of international trade, we can't really consider the full impact of industrial decarbonization of a single country without considering what other countries are doing. And you published a really nice paper that cautioned, or that considered, let me say, the risks associated with decoupling from China on decarbonization enabling technologies. I was wondering if you could offer your thoughts on how we manage this industrial decarbonization transition in a manner that simply avoids shifting burdens elsewhere, that we're not playing kind of whack-a-mole with this challenge.
That's, I think, a very important and complex topic, and for almost more than a decade, actually almost 2 decades now, we've been working in the modeling community actually to sort of understand how much emissions are embedded in industrial product consumed domestically, but also for export, and then understanding what that means for the decarbonization challenge. Also, I think one of the things that models have struggled with is actually appropriately capturing location incentives. So often you have these Armington assumptions in, for example, CG models, where you have a fixed share of product that you're exporting, and there's you don't have the ability to really substitute. You don't really know what that's going to look like in the future if you're so I think one of the things that our most recent paper showed is actually that embedded in the global challenge are also some opportunities to work together. So there are risks from sort of decoupling, because these supply chains, particularly if you think about kind of the 2 decades ago, China really entering the World Trade Organization, becoming a major center for the production of many industrial goods, and those have it being part of global supply chains. Also, other parts of the world providing raw materials into those supply chains. So again, these are very interconnected webs of production and consumption. And so as we design domestic policies, I think there are a couple of things we need to think about when we're trying to make sure that we're not playing whack-a-mole, as you said, that we're kind of creating an incentive for everybody to kind of step up and not relocate their emissions, but simply decarbonize domestically or in the places where they now want to source from, ensure that they're the product that they're sourcing. And I think there are some steps in this direction, right? So you have emissions trading systems in the European Union and in China for electric power that will soon be extended to iron and steel and other industrial products. And in those discussions, there is a very deliberate conversation about how to both capture embodied emissions as well as make sure that any imports of industrial products are also that the carbon in those products is accounted for through perhaps a border adjustment mechanism, and that's certainly in the cards in Europe, under discussion in the United States, and thinking about sort of, to do a border adjustment mechanism, which really says we're going to count the carbon in the industrial product that is coming in, and we're going to adjust through some sort of pricing mechanism what you will have to pay to source that otherwise perhaps less costly input. When we think about that, I think we always sort of want to start from the premise of how do we treat our domestic companies. And in the United States, that's you have a discussion around, do the patchwork of current climate policies across the U.S. comprise a system on which we can build a robust border adjustment mechanism? How do you do that if you don't have a single national carbon policy, as you do in the European Union region? So I think so these are some of the conversations we have to have, and then we have to look at different industrial sectors and how we count. For example, is steel product of a certain grade a single product, even if you have very different production technology mixes in, for example, in the United States, most of our steel making uses scrap and electric arc furnaces, about 70%, 30% is still the integrated route, but in China, it's almost flipped, right? The vast majority of the production of steel is in a blast furnace. So you think about sort of how do we think about the kinds of incentives that a border adjustment mechanism would create. I think it's important to count carbon around the world consistently, right? So reductions in carbon emissions should not be sort of are scientifically, and also should not be sort of geographically differentiated. And so we need to think about working towards a global trade policy that recognizes that. And also, I think one of the things that I'm often hearing is that, and this kind of goes back to the, if we think about some of the risks of decoupling from China and working on these technologies, I should say, we need to be, I think, very nuanced in terms of how we think about our strategy. So it's not going to be the same if we're talking about, wind turbines and solar manufacturing. They're a very different animal than, say, industrial carbon capture and sequestration. So, I think there are real opportunities sort of as we design our policies to also engage on the R&D side in the industrial sector, find ways to collaborate so that we can move forward the frontier, the innovation frontier, and demonstrating some of these technologies, getting that one first, second, third of a kind plant up and running, maybe even through parallel or integrated collaboration, so that we don't run into the kind of situations of, I think there are spillovers in terms of trust, in terms of even as we might be onshoring manufacturing in different parts of the world, being sure that we have a shared view internationally of what the R&D needs, the technological needs, and the policy needs are, and crafting that together is a real opportunity. So I know that was a lot of ground to cover, short amount of time, but
no, I appreciate this greatly. When asked a question of how do we the international community get this right, I would expect you need to give a full answer. One thing I would like to push just a little bit further. So we deal with this heterogeneity of materials, of different processes to produce our materials, the materials embedded in products. When we think about border adjustments, can we get it right or close enough to right with just the big materials, or how far down the list do we need to go in the modeling community to properly give service, to properly reflect this heterogeneity and these needs? Can we do it with just the big things, or do we need to have quite a list to do this right?
Do you want me to take a stab at that?
Please, Chris, please.
I think there's a term in consulting called 80-20, where you get 80% of the problem done with 20% of the time, and then 80% you then spend 80% of the time solving the last 20%. I think there is a strong argument for getting steel right first, right? Getting steel right first, getting cement and concrete right. In chemicals, there's 7 big feedstocks that if you get those and you get the carbon, hydrogen, oxygen decarbonized in those, and then especially, hydrogen for fertilizers and what have you, there's a list of about 10 things. If you do those in your models, if you get those right, or it's even 5, you're capturing much of the problem. It gets a whole lot more complicated when you start all the various heat needs at various heat grades and what have you. And that starts to become very, I'm more than willing to be argued with, but I think if you get, you get, if industry is directly 7 odd gigatons and 14 odd gigatons, including all its heat and electricity needs, you get about 5 to 6 of that if you tackle those first ones right. But I'm more than happy to be added to by the other panelists.
Yeah, I think I'm glad you jumped in, Chris, because you have a huge amount of knowledge in this space. I would also say that I completely concur. There is an opportunity, though, for handling, let's say, that other portion of energy use in a little bit more of a rigorous way. So, in the industrial sector, we long have used the term cross-cutting technologies. These are things like motor and pump system, boiler and steam systems, CHP systems, compressed air systems. In most plants that have these technologies are generally, pretty small, but there are many of them, right? So what that does is it creates kind of the opportunity for scaling up solutions and technology learning. And we go back to the electric boiler example. We can model with, reasonably well how steam is used, the different archetypes for steam use that could apply to, every variation that's out there, or most of them, in food and chemicals and this and that, right? So that level of detail would provide a lot of benefit. It's a bit beyond what we do now, but it doesn't get into all the various weeds of how steam is used in every single subsector, right? Same thing with motor systems, same thing with pump systems. And the reason, we need to think about doing that is energy efficiency has, long been called the first fuel, and it's still really important. If you look at most industrial decarbonization plans, while we develop and invest in and demonstrate and pilot all the future technologies like electrified, hybrid hydrogen steel and so forth, right? We need to continue making progress on decarbonization. So efficiency gives us that kind of, early momentum, but it doesn't happen on its own. In the US decarbonization plan that was put out by the Department of Energy a few months ago, most of the early gains out to 2050 are coming from energy efficiency. And that's sprinkled around a lot of plants in a lot of different industries, organized around some core areas like steam systems and pumps and motors and compressed air and so forth, right? So in order to tap that important momentum and to get those early savings, models need to have a little bit more granularity on, that broad category of other energy use, because the more efficient we make those plants and the more those technologies are adopted, their costs come down, our learning goes up, we can produce more case studies, there's better, information for best practice sharing, so that, plants can begin to tackle the easy stuff, all of them. So if there's one concern I've had with all the great progress we're making in industrial modeling over the last decade, is that most of the focus is on the really big picture, game-changing emerging technologies. And that's certainly, well warranted, right? But we seem to be losing a little sight, some of our insights on efficiency and how important that is in the near term, because that's something we can enact today. We know how to do it, we've been doing it, but it needs to be accelerated. So I would argue that a little bit more granularity, a little bit more focus, maybe, a renaissance in the energy efficiency movement in industry is needed, so that we can get on the trajectory that's going to help reduce demand, so that when those big technologies come, they bring us to net zero.
Well, one of the challenges that I've seen, Eric, in modeling efficiency, if we're operating under a cost minimization modeling framework, many of the opportunities, or some of the opportunities, I should say, for efficiency look cost effective yet aren't adopted. How do modelers effectively represent that phenomenon, where on a strictly cost minimizing basis you should be adopting these efficiency measures, but we don't see it happening in practice?
I mean, I'd love to hear from the other panelists. I'll just give a quick answer, and that is, the cost structure for technology adoption isn't just all about energy savings, right? So if you have to retire a piece of equipment early, then perhaps you're taking a hit on your finances. If there are other barriers, so if you change one technology and it requires you to change 6 others, sometimes that's missed in the calculus for calculating the energy savings. And frankly, we all know that there are cost-effective technologies that are out there, but if we're not ready to adopt them yet, because my boiler or my motor system is in perfectly good working order and I'm writing off that investment, it's not that it's not cost effective to adopt that energy efficient option. That's true, but it's not cost effective today, right? I'm going to wait 10, 15 years until the next upgrade or replacement cycle to do that. The other thing that could be done to really reinforce how cost effective these technologies are is start putting numbers on the co-benefits, right? Often you save maintenance costs, often you reduce emissions, often you save labor costs when you adopt efficient technologies. Those don't go into the numerator of that, the cost ratio, right? The cost per unit of energy saved. When you factor those things in, the technologies get even more cost effective often. So that's kind of the counter argument to maybe we need to get better with the numbers to make an even more compelling case. So I will adopt, that new technology earlier.
Anything to add, Valerie?
I mean, just building on that, I think we always need to be iterating between sort of the model and the real world. And I feel like we have really done an incredible job over the last 20 years in starting to do that in a more disciplined fashion. When I started working with, again, admittedly, these more aggregated top-down models, the energy intensive sector was one sector with with a set of energy inputs, averaged, and prices attached to those. And at the same time, though, you did have in those models, you can capture efficiency and or at least price-induced efficiency improvement. You have to make assumptions about the sort of long-term autonomous efficiency improvements, and then you can also sort of look at the at how different sector demand changes with opportunities to decarbonize. But there really weren't that many opportunities often built into these models, and you might build one out at expense of another. And so I think one of the things that in working with China for the first time, it was actually given the very large share of energy use and the direct use of coal in the industrial sector. It really gave us a strong rationale as a joint team to work on separating out the industrial sectors into individual sectors. And then you take iron and steel, and within that you have an incredibly, again, complex set of processes. Do you model ore beneficiation separately from the blast furnace step? Do you have a blast furnace and an electric arc furnace fleet? So I think these questions about what level of detail you need, I think just need to be had constantly with an understanding of the state of the practice, and often I think in engagement with practitioners as well, in terms of what information do practitioners need in order to what would they like to see in a model in order to believe it, in order to be willing to make policy around it and feel comfortable about, for example, putting in place a border carbon measure. So I think that these are real challenges for modelers, not just in terms of the representation of technology, but also the representation of the jobs impacts and the location of production as that is projected into the future.
Well said. And kind of returning to this idea of what do practitioners want to see in our modeling, and I guess any end user. Chris, could we explore your experience with as the lead author for the industry chapter for the IPCC report? I can only imagine that this was a particularly challenging chapter given the heterogeneities that we have just walked through. And I'm wondering if you could share your thoughts on where the greatest points of debate were in working on that chapter, and where you see the greatest opportunity for the macro energy system community to help inform future work in that space.
Yeah, no, I'd be happy to. Just a brief note to the previous conversation. The real world does not allocate capital according to optimization models, right? They use they use computation. They prioritize projects. They use internal rates of return of 12 to 14%. They're expecting failure. They're trying to meet sort of equity returns of 4 to 6%. They know things will fail. An optimization model operating on a sort of 4 to 6% discount rate is not going to tell you how real firms working with capital intense projects are going to choose between them, and we have to accept that. If we really want to create policy to move those projects, we have to work like they do, not in an optimization framework. So sorry, then I'll come back to your question.
No, appreciate them.
It's interesting, but the industrial chapter authors, like, we're all familiar with the idea of get all the technologies in there. And I have a project at Columbia to build an open source database of all the available technologies for steel, cement, chemicals, what have you. Want to make it available to all modelers, what have you, at its highest level disaggregation. And so you build all that stuff in. But where the most uncertainty was, and I wouldn't call it disagreement, is much further up the chain, right? Like when you start thinking about demand, how much steel will India really need, right? In high, medium, and low, how much steel will Africa need to develop? Things like circularity and material efficiency. We couldn't even come to, there are debates about where the boundaries begin and end between circularity and material efficiency. And the IEA has done some amazing work. I think it was initially started by Eric, actually, going, steel and especially cement are just cheap. They're really reliable, effective, and robust, but they're super cheap. So why not overbuild with cement? And the IEA, with the fairly conservative numbers they're using, is that by 2050, 2060, if you just think about cement steel use in a building or an infrastructure, you can cut its use by 25% odd. We overbuild things. Concrete can be made better if you use multi-size aggregates and dispersants. You can make a concrete wall, it's this wide, this wide, and it'll do the same job. Things like, we haven't factored in things like maximizing cementitious material substitutes. And there's a whole new class of these things that meet building codes in the West, such as LC3 cements, where it's 1/3 ground limestone, 2/3 calcined clays, that can cut the amount of clinker in use in half. That would just cut the emissions in cement in half if structural engineers and architects chose, and the construction companies chose to use them. And the performance is like, they meet the performance standards, right? In terms of circularity, we have a lot of way to go to using our iron scrap stock better, sorting it more carefully at end of life by alloy, making sure it doesn't oxidize, making sure all the copper comes out of cars and what have you, so that it's high a purity as possible before going into an electric arc furnace, right? So there's a lot of uncertainty in terms there, like, what's the high level demand level, high-end demand level, end-use demand level that needs to be met? What are the material efficiencies that can be gotten out? What maximization of circularity can we do before we even get to sort of electrification and process changes with existing technologies, and then doing process changes with lower TRL technologies, and then at the end moving on to things like CCS, right? So it's those early things that we're like, there is so much work to be done on sorting that out, and the policies needed to do it, because you're not talking about a few industrial firms and changing the processes. You're talking about architects, you're talking about building codes and building codes regulators, getting structural engineers on board, getting construction companies on board to take all those early gains. And a lot of this is analogous to the energy efficiency debates that we had through the 70s, 80s, and 90s. Why, Emory Lovins was saying, why don't we can get factor 10? Well, we got maybe factor 3, right? Because of all the sort of transactions cost and, and the efforts to change the behavior of millions of agents. So.
Great point. I'd like to try to unpack this idea of dematerialization a bit more. And, I hear you, materials are cheap, we overbuild, the incentives aren't there to trim that fat. Assuming that we don't want to make cheap materials expensive, assuming that that's not the mechanism we do, but maybe that's a poor assumption. What are our levers? Is it building codes? Is it getting into undergrad classes and training our structural engineers to recognize this? It seems like a very tricky thing to overcome in practice.
I'll go first, and then I'm sure Eric has things to say because he was part of the demand chapter. A lot of this is, well, just allowing it. It's got to be allowed in the building codes, right? And so in the U.S., I know, you've got building codes at the, city, state, and federal level, where it's some of those building codes may actually be in conflict with the performance-based building codes, where you have to use 95% OPC, but the performance code will say, yeah, you can use 50% LC3s, it'll work just fine. Architects are the first. There's an interesting thing where architects design a building, right? Then they sign off on the drawings and they hand it to a construction company, and then they never see it again. Right, and then the construction company doesn't, they hand it off to a builder, and then there's this weird, there isn't there isn't like a digital paper trail from the architect through to the construction and operation of the building. And a building that may have been designed ultra low emissions from a material and energy point of view may become quite intensive by the time, the structural engineers, the construction companies, and the builders and the operators are done with it, right? So we don't have this end-to-end chain. And it's a lot of this is education and awareness and getting the, people who buy buildings and rent buildings, telling their real estate developers that they want them, that they even know it exists, or it's something they can ask for. It's probably one of the harder problems in industrial decarbonization.
Eric, I'd love to hear your thoughts on this, but I just exposing my ignorance. Is the challenge in the building codes that we are required to overbuild, or is it that they're allowed to overbuild? I mean, so is this something where before we can do this, we need to change the building code, or building codes are a mechanism to do this? Could you help me understand
I would
better?
say building codes are a mechanism to do this. I mean, there's the overbuilding generally comes down to some of the factors that Chris mentioned, right? I mean, there are always factors of safety and design. If we've been building buildings the same way for decades and it works and it reinforces the codes and it provides the service in a way that's very robust, then sure, we'll use more materials as sort of a factor of safety. But that's a pre-Paris Agreement world, right? Net zero world, we need to take a much closer look at every ton of materials we put into the built environment or into our appliances or cars, you name it. And that was really the goal of the demand chapter for the latest IPCC report. So I worked a lot with Chris in cross-chapter collaboration. So the point of the demand chapter, first of all, it was wonderful that the IPCC gave visibility to demand reduction as its own dedicated chapter. This is the first time this happened. But the charge of the authors was to find the evidence basis for reducing demand in the first place, and how much of an opportunity could that present for getting to net zero. And our findings were that it's an enormous opportunity space, right? If we just use less steel, less concrete, less plastic, in the first place, the decarbonization challenge on the supply side gets a lot easier, right? You have to produce less. But there are all sorts of challenges. And you asked Jeremiah which stakeholders need to be at the table. Frankly, it's all of the above, right? We need architects, we need city planners, we need building engineers, we need materials engineers, we need producers, and so forth, right? The good news that I'm seeing is that those stakeholders are beginning to sit at tables now that we have things like science-based targets. We have buy clean policies at the federal, and right here in California, we have a buy clean policy that'll place a limit on the embodied carbon of construction materials and so forth, right? So there's now, there are fora and there are policies and forces that are bringing those stakeholders together. And what I see now is one of the challenges in our field as modelers is bringing all that information together so we can produce the numbers that shine a light on the opportunity space. And it's also been really great to see that happening. So Jeremiah, you come from the LCA community. That's one of your longstanding thrusts, right? So what's happening is, energy modelers and climate modelers are beginning to work with the life cycle analysis community. They're beginning to work with, the building design community, because to capture all of these opportunities, we need to capture the full life cycle system. And that means, integrating data from a lot of different sources to track how those materials flow and to find the leverage points, including, how materials are used and how we can reduce them. And that's happening. That work started before I arrived. I had the chance to help accelerate it, but even since then, they've been doing a huge amount of work, but it's still early days. But those stakeholders, those data sources, those modelers are coming together. And I think the more we can put numbers on the opportunity space, the more I think impetus there'll be for stakeholders to get together and policymakers to begin asking, why can't you do this? Why can't you do that? What if we tighten this or that? And I feel like that's happening.
That's great. Thank you, Eric. Valerie, do you feel like this discussion is similar in a developing country context? Is China experiencing the same overbuild and I guess opportunity for dematerialization? Are the mechanisms for resolving this similar? Any insights there?
Yeah, I mean, I think there are a lot of similarities in developing country contexts. The main difference that I see is, first of all, often the energy mixes and the maybe the sharp importance of cost, although cost is important everywhere. And let's be clear, it's in places where there is abundant domestic coal supply. I think there is an interest in using that in different ways, and so that directly plays into the carbon footprint of the industrial sector. But it's very location dependent. It's also, I think there is this interest in design for affordability. And I would argue in the developing country context, I think, we've spent a lot of time characterizing kind of the on-the-ground implementation of policies in developing country contexts that have been designed to incentivize everything from energy efficiency to deployment of new technologies to fuel switching. And I think one of the things that comes up is that, this implementation challenge, so that in a model, you might simulate a policy and it's perfectly implemented in that setting, right? Now, in the real world, I think there are a number of interesting frictions that come up that aren't necessarily taken into account. And one example is just in the Chinese context, in a field experiment that we did, we learned that actually one of the things that meant that, that affected the way firms manage their, in this case, mainly electricity use in manufacturing, metal manufacturing, was actually there were inefficiencies in the selection of tariff at the level of the grid company. So you had some kind of time of day pricing, but that you also had to pay a voltage charge, and you had to report that correctly to the grid company, and that was sort of never checked and not a function of someone within the firm. And so if you sort of missed that, you would really miss the fact that many of these companies were actually paying more than they needed to for electricity. If you correct those types of distortions, then you actually go in the wrong direction because electricity is essentially cheaper. And so I think there are situations like that have been, as an example from a developing country setting. I think we need to be looking for those types of sort of ways that the institutions sort of cross each other and undermine the incentives for real change that come up everywhere, from the CHP examples we've discussed to some of the discussions of how you sometimes have competing policies. And so I think and I would say that for modelers and a very empirical grounded perspective, I think this is what I meant when I said iterative, because of course models aren't going to capture everything, but you need to have I think what models do really well is they provide they are often used and looked to as a decision-making tool and as a reason to take a decision or to not take a decision. And to the extent that those models can reflect conditions on the ground, that's great. They won't be perfect, but they're still going to be used by different decision makers. So I really love the idea that we've just discussed about having sort of multiple stakeholders providing input on the use of models and sort of what and also iterating between that and the realities on the ground.
Great point, and this is a great segue to a question from Dr. Wyant. Chris, would it be desirable for MES modelers to collaborate more with the sustainable finance community about actual required rates of return and also how those might be lowered?
No, absolutely. That's a huge question. We could be here an entire other webinar talking about it. But how do you get industrial projects built, right? There's an upfront capex component. There's an ongoing component attached to industry, like energy and materials and labor costs and what have you. And it's all different for first or third of a kind versus something that's been built 50 times. I'm looking at John's point here. Yes, I think we should work with the finance. I heard a quote yesterday from Larry Fink of BlackRock. We simply do not have a global mechanism for moving the amount of capital we need to the developing and emerging world in order to get clean electricity systems built, clean industrial systems built, clean transport systems built, because the capital requirements are absolutely enormous, and we've simply never moved that amount of capital internationally and from north to south before, and we need to figure that out, and that is the expertise of the finance community, and I think that needs to come back into the modeling community. There are several types of modeling teams that actually try to simulate the capital allocation or capital prioritization mechanism more accurately than just pure optimization, and it's a whole sub part of the modeling community. It'd be nice to see some of those lessons kind of proceed out into the rest of the modeling community. And this is a very active discussion, and we have a lot to learn. We have a lot to learn and build in terms of these global, national, and what have you mechanisms to get this job done.
Great, thank you, Chris. I feel like domestically, I have seen with the bipartisan infrastructure law and the Inflation Reduction Act, a lot of attention paid to the implications on the power sector itself. Are there, I guess, what are the important aspects of these new policies in relation to industrial decarbonization? Where do we think that we'll see the most change as a result of these policies, if any?
Valerie, you want to go first?
So I can just sort of speak to what this is looks like from the perspective of a region that is very specialized in industry, oil and gas here in Southwest Pennsylvania and tri-state region. So a lot of the opportunities here center actually on the funding that is, or at the federal level, there is a lot of interest in going for the hydrogen hubs funding, the carbon capture demonstrations, and the grid resilience funding. We're also seeing on the industrial demonstration side, the money both from Bill and IRA that has become available in the through OSED, the Office of Clean Energy Demonstrations, DOE, that I think is going to be transformative on the demand side as well. And I think the challenge is to get the sort of supply side focused policies and the demand side focused policies to work well together, and to figure out ways to evolve the current incentive packages to be more agnostic towards the decarbonization solution. So we have $3 per kilogram of hydrogen as a tax credit. That really makes it look very attractive to focus on hydrogen as a solution in steel making rather than some of the electricity-based or hydrometallurgical processes or electrowinning solutions. And in the long term, that will matter. I mean, the near term, maybe it's a prescient that the coal train is just going by outside my window. I don't know if you can hear it, but I do think that we have a real opportunity to, especially in places like where I'm sitting, to transform some of our existing energy infrastructure through these bills. And the question is just how to get kind of the mix right so that we use this funding wisely.
Thank you, Valerie. We are almost out of time, and I wanted to make sure that I asked this question from an anonymous attendee who is interested in getting involved in the space, but I think is not quite sure where to start. So asking, are there workshops, certification programs for energy modeling, for decarbonization? How does one get their foot in the door into contributing to these efforts?
That's a great question. I'll try to go very quickly first. So, I mean, I'm not aware of any workshops that train researchers in how to model the industrial sector specifically, but there's certainly, workshops out there on energy systems models. So I would say the first step would be understand how the energy systems models work and maybe get your hands on one. There are some open access models like Open Energy Outlook here in the US. There are databases that Chris and others are working on to give information about industrial technologies. Get a sense of what the modeling approaches are, what the data looks like. And then, like most of us, we had to learn about the individual sectors and the opportunities to know how to use those models to represent the kind of changes that we wanted to model, essentially. I would say don't get bogged down in trying to understand every single aspect of every industrial plan and every technology. I've been doing it for 20 years, and I'll admit I don't, right? You focus on the 80-20, you learn about the core systems, the core challenges, how modeling works, and there are a lot of great resources out there for getting your feet wet. And then it's just, you jump in and you start doing it, and that's the best way to learn.
Thank you so much, Eric. We are out of time, but I greatly appreciate Valerie, Chris, Eric. I really appreciate your willingness to sit on this panel. I know that I have learned a lot in this hour, and I could have continued this for another hour, but we wouldn't ask you to sit on such a long panel. But thank you so much for your willingness to participate, share your expertise. I am sure that all of the participants who watch this panel feel the way I do. We appreciate your time.
Cheers all.
Thank you. It's a lot of fun. Thank you.
Thank you.
Thank you, Polly.
Thank you. Bye.